Okay, ladies, let's start. Okay, I'm gonna focus on probability. Well, actually, if you think about what we've been doing, it's all about probability. So we've been looking at mono and dihybrid crosses. We've been setting up these Punnett squares, and the Punnett squares represent, the odds of getting something. So in this scenario from last time, if we have a cross between two guinea pigs that are heterozygous for black and heterozygous for short hair, what are the odds of getting offspring that has brown hair and long fur? So how do you read this chart? Well, you see there's 16 possibilities, right? And only one, right over here in this corner, is a guinea pig that has brown hair with long fur. So this does not mean that you're going to have 16 little guinea pigs, and one of them is going to come out with brown hair and brown long hair. It doesn't mean anything, other than it's just 1 in 16 chance. Okay, so you got to understand the difference between like observed and expected. In other words, what does probability say, and what do you actually get? All right, that's what we're going to talk a little bit about today. So we're going to do a bit of math today. Because you don't need to use a Punnett square. I'll show you that. You don't need to use Punnett squares. The math I'm going to show you is pretty basic. It's all you need to know is how to add and multiply. That's it. So if you can add and multiply, you should be able to do this. The third thing you need is your big manly brain. Okay? Or womanly brain, in your case. Alright? So, logic. So I'm going to show you, we're going to start really simple. Because we're going to start with a very simple scenario, because that's, you should always start with something simple. So we're going to talk about how to make predictions in genetics using two tools. One is called the product rule, and it's pretty easy. It's basically, you look at an event and you figure out what are the odds of getting that event through multiplication of a series of events. So, like, for example, if I look at a coin, right? Coin, unless there's something funny with a coin has two sides, heads and tails. And the odds of getting heads is 1/2. The odds of getting tails is 1/2. So the product rule is, let's say I'm asking for a particular sequence. And there's only one way to get that sequence. What are the odds I'm going to get that outcome? So I'm going to ask a very simple question. What are the odds I would get 2 heads? There's only one way I can get 2 heads on 2 coin tosses. The first coin toss has to be a head, and the second one has to be what? Is there any other way? No. There's no other way, right? So the product rule is, what are the odds of getting one event times the odds of getting the other event to get your outcome? So what are the odds of getting the first event? What are the odds of getting heads? 1/2. What are the odds of getting heads again? 1/2. So it's just 1/2 times 1/2. So it's a 1 in 4 chance that we get heads. Now, if you think about, for example, like a Punnett square, Punnett square would actually give you the exact same prediction. So let's actually show that. So if you think of a Punnett square, because you can think of a coin like a genotype. If you think of a coin as a genotype, you have 2 possibilities. A coin can give you heads or tails. So a Punnett square will predict this. It is a very awful square. This is what a Punnett square would predict. You could get this combination on 2 coin tosses. Heads, heads. It's possible, right? But you could get, first coin could be a head, second coin could be tails, or first coin could be tails, second coin could be heads, or you could get 2 tails. Those are your 4 possibilities. What are the odds of getting heads, heads? 1 out of 4. And what did we say it was according to the product rule? 1 out of 4. So this is just a different way of doing it. Okay? So let me show you an example of a very basic question. Okay? So what are the odds of having 3 girls? You have 3 kids. What are the odds that they're all girls? Well, there's only one way to get this outcome. There's only one way to get 3 girls if you're having 3 kids. What would that be? Well, it would have to be first baby is a girl, second baby is a girl, third baby is a girl. Is there any other way to get this? No. Okay. What are the odds of getting a girl? It's pretty much 50%. What are the odds of getting a girl? 50%. What are the odds of getting a girl? What are the odds of getting... So now we use the product rule. Product rule says 1/2 times 1/2 times 1/2 are the odds of the sequence, which is 1 out of 8. Very easy.
I don't like it.
Very basic stuff. Okay?
Yep.
Now, we could say, what are the odds the 4th child is a girl? What do you think the answer is? Some of you think it's 1 out of 16? Chantal, what do you think? Should be 1 out of 2. Read the question carefully. I'm not asking what are the odds of getting 4 girls. I'm just asking what are the odds the 4th child is a girl. Read the question carefully. If I change the question, so the answer for this is just 1/2. The odds of getting a girl is always going to be 1/2. Regardless of how many girls you have, it doesn't matter. This is where, by the way, gamblers get into trouble, because they have a streak of bad luck, and sometimes they're playing a game where the previous events have no outcome on the future events. Like if you're playing roulette, what you did in the past is not going to influence what you're going to do in the future. So they think, well, I had a streak of bad luck, my luck's going to turn. No. What's going to happen in the future has nothing to do with what happened in the past. Now, if you're playing cards, it's different. Because as you're giving your cards, it changes the deck, right? But in this case, if I have a girl, initially, no, I can't have a girl, I'm a guy. But if, my wife had a girl, the odds of the second child's a girl is still 1/2. If I change the question and said, what are the odds of getting 4 girls? Then it would be 1/2 times 1/2 times 1/2 times 1/2. Okay? So just be careful, which is 1 in 16. Yeah. But that's not what the question is asking you. So, just like yesterday, where I didn't read the question carefully, and Breeza called me on it, make sure you read it carefully. Now, what if we have more than one way to get an outcome? This is where the sum rule comes in. Now, math, what is sum rule? What do we mean by sum? We add it up. So, the sum rule is, what if we have more than one way to get something? What we do is we use the product rule for each possible sequence, and then we add up. We just add it up at the end. So I'll show you an example. What are the odds if I give you 2 coin tosses, you get 1 heads and 1 tail? What are the odds? 50%. Okay, now why? Well, here's the thing. You could get this scenario where the first coin toss gives you heads, and the second one gives you tails, and the product rule says that this sequence, tails, heads, is 1 in 4. But there's another possibility, which is maybe you get tails first and head second. And this sequence is tails, head would be 1/2 times 1/2, which is 1/4. But because there's 2 possibilities, we just simply add the 2 sequences up, and 1/4 plus 1/4 gives you 1/2. Now, if you notice something, the Punnett Square predicts the exact same thing. So remember I showed you that Punnett Square for a head, tail, cross, head, tail? How many head, tails do you see in the sequence? 2. There's 1. It's still 1 head, 1 tail, right? It's still 1 head, not 1 tail. Now, Claudia brings up a good point. if the question is worded slightly differently, if I say, what are the odds of getting heads on the first coin toss and tails on the second one? Then it's 1 out of 4. Right? Because there's only one way that's going to happen. But if the question says, what are the odds of getting heads and tails, but not in any particular order, then it's 2 out of 4. So let's look at an example of a question, okay? So let's think about something like this one. What are the odds of having 2 boys and a girl? All right? So let's think about the sequence. Okay? You got it? First thing I would suggest is write out the possibilities. So here's one possibility. Boy, boy, girl. That's one sequence that's possible. What's another one? No, but then you won't have 2 boys. So, girl, boy, 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 girl, boy. Okay. Are there any others? No.
Well, if the beats were like B1 so if it was B1 and B2, you could do B2, B1, G.
Yeah, you're making it way more I don't know what you're talking about. So this is it, right? No other possibilities. Now we consider the odds of each sequence. So what are the odds of getting boys? 1 boy. The odds of getting the first. So what are the odds of first child is a boy? 1/2. What are the odds of second child is a boy? 1/2. It's always a half, right? The odds of getting a particular gender is a half. So this sequence is 1/2 times 1/2 times 1/2, which is 1 out of 8. This sequence will be the same, because it's still 1/2 times 1/2 times 1/2, so it's still 1 out of 8. This sequence is still 1/2 times 1/2 times 1/2, and that's still 1 out of 8. But see how there's 3 different ways to get 2 boys and a girl? So now we use the product rule for the sequences. Now we use the sum rule to figure out our answer. So we would say, okay, well, what's 1/8 plus 1/8 plus 1/8? 3 out of 8. There's a 3 in 8 chance that we'll have 2 boys and a girl. Okay? 3 in 8 chance. I am recording this. Now, what I'm going to do is I'm going to give you a question that, I'll be honest with you, has given students some tremendous difficulty over the years. Only a few people have ever gotten it. So I'm going to give you this question here. I'm going to pause the video, and then we're going to take it up. So I'm going to give you some time to work it out. All right? In groups. So I need you guys to think about this question. And then we're going to go over, okay? So if you don't get it, we're going to go over it. So here's the question, okay? We have Marie and Tom. They're not related. And each of them had a brother that died of a disease called Tay-Sachs. In Tay-Sachs, genetic condition where the brain cannot break down certain substances. I can't remember the actual substance now. I believe it's fat, but don't quote me on that. And the brain accumulates these toxic substances, and it ends up being fatal. The baby does not survive past about 4 or 5 years of age. So someone with Tay-Sachs does not become an adult that can have babies. Okay? So Marie and Tom obviously do not have Tay-Sachs. But well, we don't know. They could be carriers. Okay? So, Marie and Tom had a brother that died of Tay-Sachs. They get married. And the question is, what are the odds if they have a child, what are the odds that that child will have Tay-Sachs? Okay? So I need you to think about what do you need to figure out to solve this question. Yes, Serena.
Do they have hereditary carriers?
You have to figure out the odds of them being carriers. So this is what you got to do, okay? I'm going to give you like a bit of a guideline. You got to figure out the odds of them being carriers, and then you got to figure out the odds of the child has a disease. Okay? All right. So I'm going to pause. All right. So let's look at this question. Okay, so let's do this. Let's do a little mental picture, okay? Here's Marie. Marie marries Tom. Marie and Tom have a child. And we want to know if they have Tay-Sachs. Yeah, I'm recording this. Okay? Now, Marie, so this is N for Marie. Marie had a brother that died of Tay-Sachs. So let's say Tay-Sachs, so let's say N is for normal. You can use whatever letter you want. And little n is for Tay-Sachs. Okay? So we know that Marie had a little brother that passed away from Tay-Sachs. Tom also had a little brother that passed away from Tay-Sachs. Now, fix that. I'm just showing you what's called, you don't need to do this, okay? But I'm just showing you like a family tree. So these two have parents, right? So, and these two have a set of parents. In other words, Marie and her brother had to have parents that were carriers. You don't have a choice there, because let's think about the logic, okay? Marie and Tom's parents survived long enough to have Marie and Tom. So that must mean we are what? Well, hold on. That must mean they don't have Tay-Sachs. Okay? But they had children, one child, that had Tay-Sachs. The only way that's possible is if Marie and Tom's parents were carriers. The only way. Okay? It's the only way. So let's think about the logic here, okay? For this child to get Tay-Sachs, 3 things have to happen. 1, the child has to have 2 little n's. Right? The child has to have 2 little n's. 2, Marie has to be a carrier. So this is the child. And this is Marie. And Tom has to be a carrier too. There's no other way that this is going to happen otherwise. If the child has 1 big N, no Tay-Sachs. If Marie is big M, oh, I'm using M here, sorry. So it should be an N. Okay. If Marie has 2 big N's, normal allele, can the child get it? No. If Tom has 2 capital N's, normal, child can't get it. So the only way a child can get it in this case is if the child has 2 recessive alleles, the mom is a carrier, and the father is a carrier. Okay, so we know Marie and Tom's parents were carriers. So, and we know the Punnett Square for a carrier cross a carrier. We know it's what? Let's do this, right? So, did this, this. There's the Punnett Square. So, Marie, what are the odds Marie's a carrier?
Oh, wait, to be fair, you have to have what? 1 N or?
1 big N, 1 little N. No. Chantal? 2 over 3.
How is it 2 over 3?
Alright, how's it 2 over 3?
Oh, they're the same.
No. Can Marie be big N, big N? She can be, right? Okay. Can she be big N, little n? Yes. Can she be little n, little n? No.
But isn't it 1 and a 4?
No, because it's not possible. If Marie is alive, and Marie is old enough to have a baby, it tells you that she cannot be little n, little n. Therefore, Marie has a 2 in 3 chance of being a carrier, not a 2 in 4 chance.
Of having the disease.
It's not possible for Marie.
But she's only a carrier, so she doesn't have the disease. She can't have the disease, she'll be dead.
Yeah, she can't have the disease.
She won't get old enough to have a child.
Tom? Same thing. 2 out of 3. So, now the question becomes, if Marie and Tom are carriers, what are the odds of getting two little n's? Well, according to the Punnett Square, two carriers cross, if the two carriers reproduce, it's a 1 in 4 chance that they'll get unaffected child. So, the odds then become 2/3 times 2/3 times 1/4, which gives you 1 out of 9.
That's exactly how we
That's
did it.
exactly how you did it.
And that's exactly why we got it right.
Alright, so I'm going to stop there. Okay? And that is the end.